In this class, I will explain some problems on continuity equation and also the concept of acceleration of a fluid particle. I will take two problems on continuity equation. The first problem states like this. So he has given the components of velocity for a two-dimensional flow, u and v, only two components as functions of x and y. U is given as 4x plus y and v is given as x minus y square. The question is check whether the flow occurs. So it's a simple question. So if at all the flow has to occur, the first basic thing is the continuity equation should be satisfied. So that is the condition. Now for a flow to exist or occur, continuity equation has to be satisfied. Since it is a two-dimensional flow, and also if you observe that u and v whatever is given, they are independent of time component t. Therefore, it is a case of a steady flow. We can get that it is a steady flow because u and v they are functions of only x and y. So t is not there. If t term is included, then we have to take the continuity equation for unsteady flow. Now for a steady flow, this is the two-dimensional continuity equation, dou u by dou x plus dou v by dou y is equal to 0. If this condition is satisfied, LHS is equal to RHS, then automatically the flow occurs or exists. Now if you find out dou u by dou x, u is given as 4x plus y, so you have to partially differentiate with respect to x treating y constant. So it becomes 4. Dou v by dou y treating x constant, it becomes minus 2y. So if you substitute that in the LHS, this becomes 4, this is minus 2y. 4 minus 2y, but RHS is 0. Therefore, 4 minus 2y is not 0. Therefore, continuity equation is not satisfied. So since continuity equation is not satisfied, flow does not occur or exist. That's all, very simple. Now in the second problem, he has given u and v and he has also w, the third component of velocity. That means it is the case of a three-dimensional flow. Once again, u is given as 2x square, v is given as xyz. You can observe that t term is not there. So therefore, it is also a case of steady flow. But we have to write the continuity equation for a three-dimensional steady flow. So since here he has given flow occurs, that means continuity equation is satisfied. So since he has given flow occurs, so continuity equation is already satisfied. Only thing is, using that condition we have to find out the function w. Now write down the continuity equation for the three-dimensional steady flow. Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Now in this u and v are known, so u is 2x square, therefore dou u by dou x will be 4x and dou v by dou y will be x into z. So you have to differentiate partially, so by taking the other variables as constant. Now if you substitute that here, so this is 4x first term, second term is xz, plus third term is not known, so we have to find out w here. So dou w by dou z, you have to keep it as it is. Now dou w by dou z will be minus 4x minus xz. Now to get w, we have to integrate with respect to z. Please note the point here. You have to integrate with respect to z and treating x and y as constants. So very important. Suppose if u is not known, you have to find out dou u by dou x, then we have to integrate with respect to x. If v is not known, dou v by dou y is not known, we have to integrate with respect to y. Like that we have to decide. Here since w is not known, we have to integrate with respect to z. If you integrate with respect to z both sides, this dou w by dou z integration will be w is equal to, this you have to treat it as constant, x and y are treated as constants. So minus 4x into z will be there because integration of a constant with respect to some variable is constant multiplied by that variable. So minus 4xz will be there, and here x is constant, z is not a constant. You are integrating with respect to z. Integration of z with respect to z will be z square by 2, as you know, plus constant of integration you are going to get. Here x and y are constants because we are integrating with respect to z. Therefore, constant can be a function of x and y. So this is how we can find out w. So as I already told, if at all you are finding, if you want to find u, you have to integrate with respect to x. If at all you want to find out v, you have to integrate with respect to y by treating the other variables as constants. So this is another type of problem wherein he has given that the flow occurs. That means continuity equation is satisfied. Other type of problem is they will give u, w, they will ask you to check whether the flow occurs or not. Right. So the next concept is acceleration. So I have told you about velocity of a fluid particle. You will be having u, v, w, three components of velocity in x, y, z directions, and the resultant velocity or net velocity or the total velocity v can be found out by root of u square plus v square plus w square. On similar lines, we can define acceleration of a fluid particle. Also, I am taking a fluid particle at p whose coordinates are x, y, z. Acceleration of the fluid particle I take as a. So this a consists of three components ax, ay, and az acting along the x, y, z directions as usual, and u, v, w, they are the velocity components in the same directions x, y, z. Similar lines, as in the case of velocity, acceleration vector can be written as axi plus ayj plus azk, where ax, ay, az they are components of velocity acceleration along x, y, z directions respectively. Ijk are unit vectors along x, y, z directions respectively. Magnitude of acceleration denoted by modulus a or a simply root of a square plus ay square plus az square. So by knowing the values of x, y, z at a particular point, by substituting the values of x, y, z, you can always find out the velocity as well as the acceleration at the required point. Now here, just similar to your u, v, w as components of velocity, you have ax, ay, az as components of acceleration. They can be found out using these expressions. So these expressions are very important. So acceleration components can be found out using these expressions by knowing the velocity functions. So by knowing u, v, w as functions of x, y, z, we can find out ax, ay, az using this. So it is very easy to remember these three expressions. You can see here ax is given by u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou v. That means you can observe that here in the numerator only u is there, dou u is there. In the denominator you have x, y, z like this. Last term is t. Suppose if it is an unsteady flow, that last term also exists. If it is a steady flow, this last term becomes 0. Now the other three terms will be u, v, w. So like that you have to remember. So numerators dou u is there, denominator dou x, dou y, dou z, dou t is there, and first three terms you have u, v, w. So on similar lines, acceleration component along y direction, u, v, w remains as it is. You can see here u, v, w remains as it is. Instead of u, you have to take v here. So dou u is replaced by dou v here in all the four terms, and denominator remains the same. So only difference is this dou v, dou u, dou v, dou w. That's all. In the numerator terms, only those derivative terms are different. Other things you can see that they are same. So az also u, v, w is same. Instead of dou u, you have dou w. So dou u is replaced by dou w. So same thing here. So same thing here. So that's all. Very easy to remember. And among this total term. The first three terms, it is called as the convective acceleration. That means the derivatives with respect to x, y, z, those three terms combined together, it is called as the convective acceleration denoted by AC. So again, you can see here I have added all these three convective acceleration terms. So first you have three terms, second you have three terms, third you have three terms, total you have 9 terms. So all those 9 terms are added, and there it is called as the convective acceleration term AC. So you can see here, if we add all these three, u is common in these three. So I can write, I can take u outside, u into, so dou, all these three are with respect to x only, derivative with respect to x only. So dou by dou x of u plus v plus w. Similarly, plus in the second terms, v is common, into dou by dou y will come, u plus v plus w will be there, then plus in third term w is common, into dou by dou z of u plus v plus w. So this is called as the convective acceleration with respect to space coordinates. If you write the acceleration, that is convective acceleration. The second part, so that is called as the local acceleration or temporal acceleration, that is with respect to time. So that means if you have these three terms, dou by dou t is common into u plus dou by dou t of u plus v plus w. That's what I have written here. In the case of a steady flow, since the velocity won't change with respect to time in the case of a steady flow, so this temporal acceleration becomes 0. So this is a very important concept. So total acceleration term consists of two terms. One is the convective acceleration term, another one is the temporal or local acceleration term. So convective acceleration is with respect to space or the position, local acceleration is with respect to time. Now coming to the another two very important two definitions. One is called as the stream function, another is called as the velocity potential function, denoted by the Greek letters psi and phi. So this is very important in kinematics because the stream function, of course, it gives an idea about how a flow occurs, and the velocity potential function gives an idea about how the velocity changes from point to point. So here, to define the stream function and the velocity potential function psi and phi, we can define with respect to a two-dimensional flow. So this whatever I have defined here, it is for a two-dimensional flow. So you can observe here mathematically I have represented the expressions for psi and phi. See, you can see here dou psi by dou x is v and dou psi by dou y is minus v. So that means if you differentiate partially the stream function psi with respect to any direction, it gives the velocity component in the other direction. So if you are differentiating with respect to x psi function, you have to get v here, but only thing is the direction is like this. So anti-clockwise is positive, clockwise is negative. So this you have to understand. So here if you are differentiating with respect to y, you have to get the other component, that is u, but it is negative. The reason is here, you just observe here, this is x direction, this is y direction, u will be there in x direction, v will be there in y direction. Suppose if you are differentiating with respect to x, with respect to this, if you move in the anti-clockwise direction, so you are going to get v. If you are differentiating this psi with respect to y direction, so to come to this the other direction is x, so I have to move like this, clockwise I have to move. So to come to this, so that's why it is taken as negative. So that is the only difference, we should keep it in mind. Then the second function is velocity potential function denoted by phi, that is also a function of x and y. So both these are functions of x and y. So that is defined like this. If you are differentiating that phi with respect to x, then you are going to get the negative of the velocity component in that direction. So here you see, in the direction x, u is the velocity component, you are going to get minus u. Similarly, if you are differentiating with respect to y, that function phi, then you have to get minus v. So here there is no change, both are negative only. So negative of the velocity component you are going to get if you differentiate phi with respect to any direction. So here it is at right angles, here it is in the same direction. So by combining these two, if you observe, by combining these two, what we can write here is dou phi by dou x is the same as dou psi by dou y, because both are equal to minus u. And second equation, this is the first one, first relation. Second relation, if you take dou phi by dou y, which is minus v, but this is plus v, therefore I have to take minus of dou psi by dou x. So these two equations, they are also called as Cauchy-Riemann equations. Cauchy-Riemann, CR equations. In mathematics also you have this CR equations which gives the relationship between psi and phi. So by using these two relations, you can always find out one function by knowing the other function. So if they give phi, you can find out psi, or if they give psi, you can find out phi. So for doing that, we need this relationship. These two relationships are derived from the definitions of psi and phi. So the above relations are for a two-dimensional irrotational flows are also called as potential flows, because only in the case of irrotational flows you have both psi and phi. So this stream function and velocity potential function exist or occur only in the case of irrotational flows. So this is the another basic concepts of kinematics. So I have explained about two problems on continuity equation, and I have explained about the definitions of acceleration, how to obtain acceleration in the three different directions, and what do you mean by local and convective acceleration. Then the definitions or concept of stream function psi and velocity potential function phi, and their relationship, which are called as, which is also known as Cauchy-Riemann equations, by which, by knowing one function, we can find out the other function.